discussing the general procedure for solving problems of motion of rigid bodies. The general procedure means the center of mass reference frame. When a rigid body undergoes a combined motion, the center of mass will move and the rigid body will have some angular velocity. When the velocity of center of mass changes, the net force acting on the rigid body will be non-zero. And when the angular velocity of the rigid body changes, the rigid body will experience a non-zero external torque. So, in center mass frame, we will take the torques of all external forces with respect to the center mass of the rigid body and equate the torque with I into alpha, where I or IC is the moment of inertia of the rigid body about the centroidal axis. Alpha is the angular acceleration of the rigid body. This is called Newton's law of rotation. The rigid body rotates. Rotation of the rigid body is given by omega. When this omega changes, it will have an angular acceleration. When the omega increases, angular acceleration, angular velocity, both are unidirectional. Both are clockwise or both can be anticlockwise. For clockwise it is in, for anticlockwise it is out. When alpha is not equal to 0, the rigid body must experience a torque about or with respect to center of mass axis. This torque about the center of mass axis is equal to IC into alpha. Then who causes rotation? Torque causes rotation, but torque about which point or which points and torque of which forces? Who causes rotation? The answer is torque. Then the question can be put: torque of which forces? The answer is external forces, because the internal force as a whole cannot produce a torque about any point. Therefore, the torque of external forces should be taken into account. Next question we can pose: about which point? Here is the idea about which point. Torque about which point of the rigid body will cause its rotation. Rotation means angular velocity. Causing rotation means change in angular velocity. Who causes rotation? Torque will cause rotation. Torque of which forces? Answer is torque of the external forces. About which point you have to take the torque of external forces? This must be the center of mass point. The answer is about center of mass, but not any other point. The torque about the center of mass of the rigid body due to the external forces only will be the cause of rotation. The torque of external forces taken or measured with respect to the center of mass of the rigid body. The torque of external forces taken with respect to the center of mass of the rigid body causes the rotation, means changes the angular velocity. Causing an angular acceleration. Torque about the center of mass is the cause of rotation, not about any other point. To justify this idea, let me take a conceptual example. If I release the pen, if I release this pen, it is falling in such a way that its angle of orientation does not change. When it falls under gravity, its angle of orientation is not changing. Therefore, this theta is a constant quantity. The rate at which this angle changes is 0, and we define the rate of change of the angle of inclination of the rod with respect to a fixed line, say x dash, as the angular velocity of the rod, and this is equal to 0. The rod is not rotating. When the rod is not rotating, alpha is 0. Alpha of the rod is 0. Omega of the rod is 0. Alpha of the rod is 0. This is called rotational equilibrium. When alpha is 0, this is called rotational equilibrium. Alpha will be 0 only when net torque acting on the rod about its center of mass will be 0. The gravity acts at the center of mass. No other force is acting except gravity. Since the gravity passes through the center of mass, it cannot produce a torque about the center of mass axis. Therefore, the net torque about the centroidal axis is 0. Hence, alpha is equal to 0. And if you take the torque of gravity about any other point of the rod or any other point outside the rod, we may not get 0. For instance, if you take this point, suppose point P, with respect to this point outside the rod, the torque is equal to mg into x in clockwise direction. This is not equal to 0. So, if you conclude that since the torque about this point of the rod or experienced by the rod is not equal to 0, alpha of the rod is not equal to 0. Therefore, if you wrongly conclude that the rod undergoes the rotation when the initial velocity of the angular velocity of the rod is 0, this mathematics gives us a wrong idea that the rod will sooner or later will attain some angular velocity. But the rod is practically, when the rod is falling, is not getting any angular velocity. Its angular velocity was 0 and angular velocity will be 0 all along its motion. Even though the gravity is acting and gravity is producing a torque about some other point outside the rod. Therefore, torque about gravity is an external force. Torque of the external force about any other point may not be 0, but we don't need that torque to decide whether the rod will experience some sort of change in rotation or non-zero alpha, or when the rod has no angular velocity and it is released from rest, whether the rod will get some rotation or angular velocity, that will be decided by a torque of external force. Even though gravity is an external force, the gravitational torque about this point is non-zero, but we should not falsely conclude that alpha is non-zero. Alpha will be non-zero about this point, but that alpha is not the alpha of the rod. That alpha will be the angular acceleration of the center of mass of the rod with respect to this point. That is different concept. Angular acceleration of the rod is the relative angular acceleration between any two points of the rod. That is always 0 because the gravitational torque is 0 with respect to the center of mass of the rod. That decides whether the rod should change its angular velocity or not. So, the cause of rotation means change in angular velocity is due to the torque of the external forces taken or measured or calculated with respect to the center of mass of the body, not about any other point. That is the root of rotational dynamics. So, tau c, but not torque about any other point. Torque about the center of mass decides whether the alpha of the rod will be non-zero or 0. So, torque about the center of mass of the body is equal to the moment of inertia of the body about the center of mass axis into the angular acceleration of the body. So which causes rotation? The torque of external forces taken with respect to the center of mass of the rigid body causes the rotation. The cause of rotation is nothing but change in angular velocity or causing an angular acceleration. So in this way, we can say the cause of rotation is the torque or torque about the center of mass of the rigid body. Let us take another example. To follow the general procedure, in general procedure, we can take the reference point as the center of mass to write the equation of rotation. And translational equation of Newton, F is equal to ma. Needless to mention, the acceleration of that equation is the acceleration of the center of mass. That is called equation or dynamical equation for translation. Tau c. Torque above the center mass causes the angular velocity to change. Obeying this equation, tau c is equal to IC to alpha. This is called dynamics or dynamical formula of rotation. You take the rigid body, the net force acting on the rigid body is supposed to be acting at the center of mass, is net force. Let it be F. And this force causes linear motion. Causing the linear motion means change in velocity of the center of mass. Let it be A. Then you can write Newton's law of translation, F is equal to m into A or AC. This is called dynamical formula of translation. So this method you are following is based upon the center of mass frame. About the center of mass, we have to take the torque of all external forces and equate the torque with IC into alpha. Alpha is the angular acceleration of the rigid body, and the net force acting on the rigid body should be equated with the mass of the rigid body times the acceleration of the center of mass, not acceleration of any point of the center of the rigid body. It is the acceleration of the center of mass. So let us take an example to clarify these two ideas: the dynamical formula of rotation, the dynamical formula of translation. Well, let us take an example. Take a rod. Let us assume that a horizontal force is acting at the end of this rod, at the end 1. Another force is acting at this point, that is f by 2. This is at a distance of L by 4 from the end 2 of the rod. The rod is placed on a smooth horizontal floor. The horizontal floor is smooth. The rod is acted upon by two forces, and another force is acting at the point 2. Is an opposite direction towards left. Let the magnitude of this force be 3f/4. If the length of the rod is L, and the mass of the rod is M, find acceleration of the center of mass of the rod, acceleration of point 1 this end, and acceleration of the point 2 the other end of the rod, and angular acceleration of the rod at the given instant. All the forces are acting perpendicular to the rod, and our procedure is general procedure. General procedure means what? Sitting on the center of mass and calculating the torque of all forces. With respect to the center of mass. This force F is producing a clockwise torque. This force is producing an anti-clockwise torque. This force is producing a clockwise torque about the center of mass. The net torque about the center of mass can be given as sum of these three torques with respect to center of mass. Tau 1 is equal to F into L/2, whose direction minus kk. Clockwise, the torque produced by this force about the center of mass, you have to take the distance from the center of mass. That is tau 2 is equal to, if this is L/4, from center of mass to the point of application of this force, the distance will be L/4. Therefore, the torque produced by this force about the center of mass is L/4 into F/2. And direction is anticlockwise or positive kk. Next, the torque produced by this force produces clockwise torque, which is equal to force into the distance. This distance is L/2, but direction is minus kk. So the net torque with respect to center of mass is equal to F L/2 kk. You take common, you are getting -1 minus plus 1/4 and minus 3/4. -1 plus 1/4 is minus 3/4. Minus 3/4, that is minus 9/4. In this way, you are getting -9 FL by 8 kk. So here we are getting -1 plus 1/4 minus 3/4. That's equal to minus 1 plus 1 by 4, that is minus 3 by 4. Minus 3 by 4 minus 3 by 4, that is minus 6 by 4. Minus 6 by 4 into minus 6 by 4 into FL by 2 kk. This will be minus 3 by 4. So we have to just change it, minus 3 by 4 kk. In this way, you have to recheck the calculations. It's very important. Well, after getting the net torque about the center of mass, we have to use the Newton's law of rotation, which states that tau c is equal to IC alpha. Tau c we got minus 3 FL by 4 kf is equal to the moment of inertia of the rod about the center of mass axis is ml square by 12 into alpha. This gives us alpha is equal to 4, you cancel, this 12 and you are getting 3 here. LL getting cancelled, you are getting L here. So alpha is equal to minus 9 F by ml kf. So the angular acceleration is clockwise or minus kf direction. Now we can calculate the center of mass acceleration by using law of translation. F is equal to m into AC. The net force is equal to this force plus this force plus this force vectorially. This force is F I cap, this force is F by 2 I cap, and this force is 3F by 4 minus I cap. This is the net force. Let us assume that the center of mass has acceleration AC, m into AC I cap. F plus F by 2, that's equal to 3F by 2 minus 3F by 4. You are getting 3F by 4 I cap is equal to m into AC I cap. Remove I cap from both sides by taking the mod of I cap from each side. You are getting the AC, the acceleration of the rod center of mass is equal to 3F by 4F. So the net force is F plus F by 2, 3F by 2 minus 3 by 4. That's equal to 3 by 4 in positive x direction. 3 by 4 by mass of the rod, that is m, will give us the center of mass acceleration, and we are getting positive result. This means that our assumed direction of the center of mass acceleration is absolutely correct. Or vectorially we can write I cap, answer. After getting the center of mass acceleration in alpha, by using the kinematical equations of rotation, acceleration of the endpoints of the rod can be calculated. Let us draw the kinematical diagram. Alpha is clockwise, acceleration of the center of mass is directed towards right or positive x direction. AC, this point 2, this point 1. Acceleration of 1 is equal to A1C plus AC. Axis of this point is A2 with respect to ground is equal to A2C plus AC. Galilean transformation of acceleration. A1C is equal to L by 2 into alpha. In which direction? Positive x direction. And the center of mass accelerates in positive x direction. That is A1. Similarly, A to C, acceleration of this point with respect to center of mass will be in this direction. That's equal to L by 2 into alpha. As you discussed in the chapter of rotational kinematics, bring the two vectors to this point and the acceleration of this point is equal to AC plus L by 2 into alpha I cap. Here L by 2 alpha, acceleration of this point with respect to center mass is directed towards left, and acceleration of the center of mass bring this vector to this point to get the net acceleration of this point too. So AC minus L by 2 to alpha I cap. We have found AC and alpha. Substitute their values in this equation or in this equation. What is AC? 3f by 4m. What is alpha? The magnitudes. Direction already you have written. Just you have to substitute the magnitudes. L by 2. What is alpha? You should not substitute minus k cap. The direction part already you have mentioned. These are the magnitudes. 9f by ml. Into I cap. So LL will be getting cancelled. 3f by 4m plus 9f by 2m. So if you take f by m common, the I cap common, you are getting 3 by 4 plus 9 by 2. 3 by 4 plus 9 by 2. Multiply both numerator and denominator of the second term by 2. So you are getting denominator 4, 4 you take common. Taking common, we are getting f by m into 1 by 4. This is 3 plus 18, that is 21. Okay. So acceleration of this point 1 is equal to 21 f by 4m k cap. It's not k cap, it's I cap. This point moves towards right with an acceleration a1 is equal to 21 f by 4m. This acceleration of this point is towards right. Let us calculate the acceleration of this point. 2. AC is equal to 3f by 4m. L by 2 alpha is equal to 9f by ml magnitude into I cap. F by m you take common, 3 by 4 minus 9 by 2. I cap. Same technique you have to apply. So 3 minus 18, this will be minus 15 by 4 F by M I cap. This negative sign or minus I cap signifies that this vector acceleration of 2 with respect to center mass is greater than the acceleration of the center mass. Therefore, this point will accelerate towards left with 15 F by 4 M meter per second square. This is A2, this is A1. In this way, we can calculate all these factors by using the dynamics of rotation, the dynamics of translation, the kinematics of rigid body. These are the kinematics. And these two are dynamics. In this way, this dynamics plus kinematics is called mechanics of rigid body, accomplished by the general procedure. In general procedure, always you have to take the reference point, the center of mass of the rigid body. Now I will tell you another procedure to solve the rigid body motion when the rigid body is pivoted at a fixed point. Let me discuss the basics or the fundamentals of the equations related to the problem solving techniques of a rigid body which is free to rotate about a fixed point, or you can say the fixed axis rotation of a rigid body.